Hello everyone, my name is Glady'S of Technical University of Kenya. I wish to make a presentation on comparative study of 2D graphene transition metal dichalcogenide heterostructures as electrodes for alkali ion batteries. This work was done under the supervision of Dr. Nicholas Makau of University of Eldoret, Professor George Amolo of Technical University of Kenya, and Professor Cecil Ouma, who is associated to both HISA Infrastructure, Northwest University, and Africa Institute for Mathematical Sciences Research and Innovation Center. The outline for my presentation is I will have an introduction, a brief literature review, a statement of the problem, methodology, results, and then conclusions of the work. So, when we talk of 2D materials, then we refer to the kind of a material that has been exfoliated from the bulk structure. And in this case, we have a mono or a few layered system of the bulk. And you'll find that by doing this, we obtain materials that usually have very exotic properties in comparison to their bulk. Among the properties that these materials have been observed to have is that they have a very high surface area, enhanced mechanical strength, and they also have a very high flexibility and optical transparency. So we have various materials that have been studied as 2D materials, including graphene and M-exins and also others. So the first 2D material that was ever discovered was graphene. In which case, graphene is obtained from graphite, and it is usually a single layer of graphite. So in this case, you'll find that it is exfoliated from the bulk form, which is usually graphite. And what we find is that it attracted a lot of attention from researchers because it was found to be very thin and to have very excellent electronic conductivity. It was also found to have very high mechanical strength and good stability for chemical agents. It was also found to be chemically inert, and it is also a semi-metal with a zero band gap. So in this work, we will be working with graphene and other 2D Tmdcs. And when we talk of Tmdcs, we are talking of materials whose formula is in the form of Tx2, in which case the T represents transition metals that are included here on our side. And these transition metals are usually combined into compound form with either sulfides, selenides, or telluride. So one characteristic of these materials is that you find that they have a very weak van der Waals interaction, and therefore this makes it possible to exfoliate them into monolayers. Unlike graphene, which has only a particular, that has been found to be semi-metals, you'll find that we have Tmdcs, some of which happen to be semiconductors, others are semi-metals, others are true metals, others are superconductors. So they have a variety of properties. So in this case, we'll be making a heterostructure for our work, and you'll find that we will be placing a layer of graphene above a layer of our Tmdc. So for example, the one we have on our screen is a graphene hafnium disulfide heterostructure, and its side view is as shown in figure B. So our interest is on electrode materials, in which case when we talk of electrode materials, we are talking of the cathode and anode of the standard battery, alkali ion battery. And The characteristics that we expect to get in a good electrode is that they are expected to have very good conductivity. We also expect them to be materials that are stable when they come into contact with the electrolyte. They are also expected to have charge and discharge at high power and also have a high gravimetric and volumetric energy. So our interest in alkali ion batteries has been allowed by the fact that the alkali ion battery technology has been unable to satisfy the demand for portable electronic devices for large-scale applications. And this has been mainly because you'll find that they have very poor conductivity and a large volume change during cycling. They also have insufficient gravimetric capacity and poor late capabilities. And in this work, these were the issues that we were addressing. So the methodology for our work is we started with the bilayers, with the monolayers of our systems, and we did this by introducing a vacuum between the layers, and therefore we were able to obtain the monolayers of the various systems, after which we made their bilayers. We made the monolayers by introducing a vacuum of approximately 20 angstrom. Then after that, we combined 2 layers of each system to obtain the various monolayers, and then we formed the heterostructures by combining each of the systems with graphene. So in the study, we carried out first principle calculations using quantum expression, and the functional that we used to describe our system was the PBE, and in all the calculations, norm-conserving pseudopotentials were applied. So we formed our heterostructure by placing a graphene layer on our Tmdc, after which we intercalated it with ions. After that, we also conducted night elastic band calculations in order to study how ions diffuse through the system. To study the electrochemical properties, we studied the open circuit voltage and the theoretical gravimetric capacity of the systems, and these were described using the equations 2 and 3 as shown on the screen. So the results. So the first thing we needed to identify was the configuration of our system, because you'll find that our system is combining a graphene and a hafnium disulfide in a Tmdc layer, and therefore in this case, since the two of them do not have the same lattices, you'll find that there was a lattice mismatch that was occurring, and therefore in this case, the first thing we needed to identify is the configuration that we would use. And this configuration, the first thing that we needed to attempt to do is to reduce the lattice mismatch, because you'll find that what happens is that the lattice if the lattice mismatch was high, then it would interfere with our system, because it would introduce unnecessary strains that we didn't want in our system. So in this case, we first formed supercells in order to be able to reduce the mismatch as much as possible. Then after that, we needed to identify the lattice mismatches, the lattice that we were going to use for our system, whether we were going to work with the graphene as the reference, whether the lattice parameters of graphene would be our reference, whether it would be those of the Tmdc, or whether it would be an average of the two for both the graphene and the Tmdc. And what we realized is that when we use the graphene as reference, then we obtained a system that had the lowest binding energy, which we interpreted, or which meant that this formed the most thermodynamically stable system. For this system, we also calculated the associated lattice mismatches, and they were found to be acceptable because in all cases, they were less than 2%. So once we identified our best heterostructure, the next thing we did was to determine the interlayer distance that was most appropriate between our two layers. And to determine this, we needed to plot the curve that we would obtain when we compare the binding energy against the interlayer distance. And when we did this, we obtained a graph, and the graph that we obtained can be seen to have a Lennard-Jones potential type, which signifies the presence of van der Waals interactions in our systems. So the indicated points refer to the optimal points of the interlayer distance, and these are considered to be the most stable points because you'll find that is where we found the curve to have the lowest energy. So we identified these points, and what we observed is that for the various heterostructures, it was between 3.25 and 3.50. And when we compare with other studies, we found this to be within an acceptable range in comparison to those. The other thing we noted is that within that range, we also had binding energies that were negative, an indication that our system was thermodynamically stable. So after this, we needed to determine the electron conductivity of our system, because you'll find that it influences the efficient movement of electrons. So what we found out was that for both the graphene and disulfide, zirconium disulfide, and the graphene zirconium diselenide, the two systems resulted in a system that had a zero band gap, while that of graphene hafnium disulfide had a band gap of 30.7 milli-electron volts. And based on this, we found that our system then would be able to conduct the electrons efficiently because the band gap that we are obtaining was quite minimal, even for the graphene hafnium disulfide. And this is a desirable characteristic for alkali ion batteries. Then after that, we needed to determine the ion intercalation and the intercalation in our system and how it was affected by the number of ions that we intercalated. So we carried out calculations of the number of intercalants against the binding energy. So when we increase the number of intercalants, we needed to study how does it affect our system. Does it still remain being stable, or does it become unstable as we increase the number of ions? And to do this, we made a plot of the binding energy against the number of ions that were intercalated. In this case, we intercalated between 1 and 4 ions. And what we found out is that except for the potassium bilayer graphene, that is the bilayer of graphene, all the other systems, even upon intercalation, we find that their binding energy still remains to be negative, which assures us that our system is still thermodynamically stable. For the intercalation with lithium, we find that all systems, even upon intercalation with lithium, all of them had negative binding energies, another indication that our systems still remained to be thermodynamically stable. So A good electrode material should also be one with a small volume change upon intercalation of ions. So we also considered how the number of intercalants affected the change in the Z direction of our system, and we interpreted this in terms of volume expansion. So in this case, we found that upon intercalation with lithium, we found that the volume change for the systems, the highest volume change was obtained in the bilayer of zirconium diselenide. So it is this one with the purple line, and you find that it obtained the highest change. Then when we look at the potassium intercalated system, we'll find that initially we had such a high increase after intercalation with the first ion, and we can attribute this to the fact that you find that potassium has a bigger ionic radius in comparison to lithium. However, we find that except for the bilayer graphene, all the other systems, upon intercalation of more ions, kind of contracts, and this assures us that our system would be expected to maintain its integrity even after intercalation of more ions. It is important to, however, note that the one that experiences a large expansion, those systems are found to be among the bilayer systems, as we can see in our table 3. Looking at table 3, we notice that for the heterostructures, which are at the top, when we look at our heterostructures, what we observe is that upon lithium and potassium intercalation, we realized that the maximum volumetric expansion was recorded in the bilayers systems, with the bilayer of zirconium disulfide. Bilayer of zirconium disulfide having the largest volume expansion in the case of lithium intercalation, and bilayer zirconium diselenide having the largest expansion for the potassium intercalated system. In comparison to other systems that have been studied, for example, silicon-based electrodes, we'll find that the expansion of the heterostructures is quite small, because looking at silicon-based, for lithium, they go up to 280. For graphite, upon intercalation with lithium, it has an expansion of 10, while for potassium, it's at 59.7, all of which are found to be higher than for our heterostructures. And this is a desirable thing for our heterostructure. Then we also did the large elastic band calculations in order to determine the diffusion barrier for the alkali ion batteries. And in this case, we tried to compare the heterostructure systems against the bilayer systems. And what was apparent is the fact that for the heterostructures had a lower diffusion barrier in comparison to the heterostructures, apart from the case of bilayer hafnium disulfide. The same was observed for the potassium intercalated system, clearly indicating that formation of the heterostructure actually improved the volume expansion, actually improved the diffusion of these systems. Another thing that we considered in our study was the electrochemical properties of our systems. And looking at the electrochemical properties, of interest was the open circuit voltage. And in the open circuit voltage, we find that positive open circuit voltage values are an indication of the possibility that we can intercalate within that system. And depending on the value we obtain, we can get a material that will form a very good anode. For example, if the range of this open circuit voltage is between 0.1 and 1.0 volts, then that material would be found to be a very good anode material. And this is what we found for potassium intercalated system. Looking at our graphs, all our values were positive, an indication that it is possible to intercalate within this system. And what we found was that the potassium intercalated system would make a very good anode, while the lithium intercalated systems, we found all the heterostructures to have an open circuit voltage greater than 1, and therefore they would make for very good cathode. Then the other thing we studied was the theoretical gravimetric capacity of the heterostructures that we considered. And what we observed is that for these heterostructures, for lithium intercalated systems, they gave quite high gravimetric capacities in comparison to what we commonly use today, which is graphite. In fact, for the graphene zirconium diselenide, it had even a higher one than for the graphene vanadium disulfide, which has been studied before. For the potassium intercalated systems, we found that the graphene zirconium disulfide had a higher gravimetric capacity that is even higher than for other materials that have been studied, and this was a positive thing for electrode material applications. In conclusion, therefore, what we observed is that the lattice mismatch that existed for our systems was between 0.27 and 1.86% for the heterostructure equilibrium geometries. And in all the cases, we were able to show that actually graphene lattice parameters gave the best system when used as the reference. So the configuration that was used for this study then happened to be the one that had the graphene parameters as reference. We also found a vanishingly small band gap of 30.7 millielectron volts in one of the systems, with the rest being metallic, and this was an indication that our material would be able to carry electrons easily. Then the other thing that we also considered was the binding energies of the heterostructures, including after intercalation, and in all the cases we were able to show that the binding energies were negative, an indication that even after intercalation our system remained to be thermodynamically stable. We also considered the activation energies for the various systems, and we found that the activation energy for the lithium and potassium ranged between 0.044 electron volts to 0.28 electron volts, and between 0.026 electron volts and 0.060 electron volts respectively, an indication that fast kinetics for battery operations are possible using these heterostructures. The other study involved the volume expansion, and we were able to demonstrate that the lithium intercalation lay between 4.85 and 6.15, while that of potassium lay between 50.48 and 54.13%. And this is an indication that our heterostructure is promising in terms of ensuring structural reputability even during use. Also, we calculated the open circuit voltage for the lithium intercalation and that of the sodium intercalation. And based on this, we were able to identify the most appropriate use for our heterostructure. We were also able to demonstrate that except for the potassium intercalated graphene zirconium diselenide and graphene hafnium disulfide heterostructures, the theoretical capacity for the other intercalated heterostructure systems was above 448 milliampere hour per gram, and this was demonstrated to be even higher than for graphite, which is presently used. In conclusion, then, we can see that the investigated heterostructure properties outperformed graphene and other Tmdcs that have been investigated for battery electrode applications. With that, I come to the end of my presentation. Some of the references that have been quoted in this work are as indicated.